Thank you, Ben. Let me quickly adjust my screen so that I have everything under control. So yeah, thank you again. Thank you for having me. Thank you for coming to my talk. It's called The Eternal Sunshine of the Spotless Programming Language. Ben already did a fantastic introduction. I'm so happy. I'm always happy when I see the TypeScript in 50 Lessons book in somebody's bookshelf. It's a beautiful book. It's nice to look at. It's nice to hold in your hands. It's also good to read, I hope. And yeah, it has become a little passion of mine to write down what I think about programming languages. Speaking of that, I want to talk a little bit about C++ before we dive deep into some of the Rust features that I personally enjoy most. And this is some sort of a subtitle, The Endurance of Pain of C++. And bear with me, I don't mean the pain that you have to endure when you are going to code C++. I'm rather talking about the pain that the standard committee is confronted with, because apparently everybody tells them that the programming language is shit. Sorry for swearing to 3 minutes in. That just happened. And I think it's a little bit unfair to constantly bicker on C++. You need to know where C++ is coming from and how it developed into the programming language that you ended up with. One thing that I can highly recommend is the video, which is linked here, called The Design of C++. It's been recorded in 1994, just a year before Java became stable, where Bjarne Strustrup, after 10 years, after a decade of C++ in production, describes his original intention with the programming language. And it was all about types. It was all about trying to create user-defined types, trying to create the relationships between those types to support large-scale programming. If somebody of you has done TypeScript, for example, that's about the same goals. They wanted to have the best of C, but improve the static type checking. If you understand the type system of C, which is, pictured here, then you know that this is a very noble goal, and people really want to have proper type systems in C++. And this is also what brought C++ on the screen of so many developers. This is why it was loved during the 80s. This is why people wanted to work with it. You had the power and the speed of C, but you had a type system that you can express yourself with, which was great for writing applications that can scale. If you look a little bit on the timeline of other programming languages that came in place, C++ is about as old as I am. It was incepted much before my inception, but the first release was about 1983. And since then, about every decade or so, people try to get rid of it. Why? Why do people try to get rid of it? Let's look at the first contestant of C++, Java. This is James Gosling, one of the creators of Java, who said that, well, working for a long time with C++, you realize that the memory management can be very frustrating because you need to do it on your own. You are in charge of having proper memory management in C++. And Java was originally designed for embedded devices. When you had to work with limited resources, this can be a problem because you need to be very disciplined in doing memory management right. They said a programming language without garbage collection was not suitable for the task they wanted to do. So what James Gosling and his colleagues did was to create a programming language that kind of looks like C++. There's lots of influence in terms of syntax, in terms of features, in terms of the object-oriented design from C++, but get rid of everything that's low level from C. So take what they liked about C++ and get rid of everything which was frustrating, which led to Java, which is a topic that we can discuss on its own for ages. I won't do that here today. Funny enough, the original working title, you know it as Oak, but one original working title of the programming language was C++, minus, minus, which tells you a lot about what the programming language was supposed to be. Fast forward another 10 years. Rob Pike was sitting together with Rob Griesemer at Google, compiling some C++ code because they needed efficient memory. Java was not cutting it, and they were increasingly frustrated because of similar reasons. They also had frustration with C++ memory management. This was just cumbersome, especially in a large-scale project. And on top of that, they had to work with slow builds. They told that, if they would have concatenated every file that they've written on, it would have been about 4.2 megabytes or something. But if you expand all the includes from the module system at the time, how you structure your application, you had about 8 gigabytes that were delivered to the input of the compiler, which resulted in tremendous compiling efforts. Also, the language was already very vast. This was around 2007. C++ 2003 was out already. People decided on language subsets to work with. If you get then another developer into your team, they need to adjust to that language subset because the language itself was just too vast and too much to understand. And this also led to a poor program understanding. You need to learn the conventions of the team before you can learn what the program is actually about. And this is something that bothered them. So they did about the same thing as James Gosling 10 years ago. And they said, let's remove everything we hate about C++, which is basically everything that Bjarne added. Let's focus on the core of C and let's make that better. And this led to Go, which is, Go is also a programming language that is highly debated among developers. I personally don't like working with Go, but I like listening to Rob Pike talking about Go. Rob Pike has a lot of great design decisions. He understands how programming languages can work, and I think the work that he did is remarkable. So go check out the link that I have here below, and also check out every video of him on YouTube. Which leads me, for the first time, to Rust. Rust, I guess, also about the same time incepted as Go, but not released before 2015, had a very similar problem at a very similar time. C++ was unmanageable. People worked on language subset. It was hard to write concurrent applications, to write multi-threaded applications. And they wanted to create a programming language with no compromise on performance. They had a garbage collector first, but they removed the garbage collector thanks to the work of Nico Matsakis. I had the privilege to talk to him about it when going with the tram from the hotel to Eurorust. It's actually remarkable what they did to bring something from academic into a programming language that is used by thousands, hundreds of thousands of people. Go check out this video, Hack Without Fear. You learn a lot about what the basic design of Rust is actually about. And lots of development, people try to get rid of pain points in C++ and try to make a better programming language. But you know what? The C++ folks are not sleeping. Actually, they are also working on making their programming language better and introduce more features. If you look at C++ now, we have things like memory safety, which is very similar to what you have in Rust. You have unique pointers, shared pointers, you have move semantics, all abstracted in respective helper types that bring you to a Rust-like experience on how you can manage memory. With type traits and concepts, you have zero-cost abstractions, which are very similar to traits in Rust, but C++ified. And also get rid of all your includes and all your header files with modules and imports. You can have fast compile cycles. You have proper structuring of your application. 40 years after the C++ inception, you finally can structure your C++ application like you would do in a modern programming language. You have an expanded standard library, arrays, vectors, and you have primitives for asynchronous programming, for concurrency, for coroutines. A concept that is also around for ages now finds its way to be a first-class citizen in the C++ programming language. Fantastic. Lots of new stuff there. Lots of things inspired from programming languages like Go, Rust, Java. They look beyond the edge of the plate. They know what's going on, and they can modify the language to something that is modern and usable. And this is even what Bjarne says when he gives C++ talks. He is very critical about the way C++ is taught, because he says, yeah, well, C++ is a huge standard. It says what's valid, but not what's useful. And people, if you go to university or to boot camps or wherever where you learn C++, you learn the C++ from 20 years ago, the C++ that I learned. And I was pretty shit at C++, to be honest. Second swearing, just another euro in the swear jar. So he urges people to teach better, to get new programmers on board in a better way with modern concepts, with proper subsets. And there's this little word again, the language subset. Focus on a carefully selected language subset. This is the key to understand good C++. And this is also something that, for example, Chandler Caruth from Google, again, 15 years after Google creates another low-level programming language. High-level programming language, high-performance programming language, which is called Carbon, which really tries to be a C++ successor. It wants to integrate well with C++. Its goal is to be a good tool that works really, really well with C++, but has a very small language, some new construct that make it modern, and something that makes it easier to reason about, easier to understand, and easier to write. So the goal is to get rid of everything that people hate about C++, have a proper defined language subset that integrates well with C++. Also look at CPP Front 2 by Herb Suttner, who has also been in the C++ standard committee for ages. He also tries to get rid of lots of technical debt, basically, that comes along with the C++ language. So Chandler really nailed it in his talk at CPP North, where he said that C++ accumulated decades of technical debt because they prioritized backwards compatibility. This is a noble goal. Don't get me wrong. Don't pick about C++ for being old and trying to cater to developers who worked with the language for ages. It's about 4 decades worth of code. This is a noble goal, but it leads to this one problem that we have, why we constantly need new programming languages like Rust, that it's not about what we can add to C++, but what we can't remove. C++ prioritizes backwards compatibility. This is a very hastily adjusted quote by the author of The Little Prince, Saint-Exupéry. I'm probably butchering his name, but it nails it. We are not talking about what we can add to make it modern, but what we can't remove. For example, like this house. This is in Innsbruck, photographed by my friend Bernhard Meyer. This has been designed by committee. You can see the decade. Those features have been added to the roof of this beautiful house right next to the main station in Innsbruck. And also, if you look about the page size of the standards, the most recent one, no, it's not the most recent one, C++ 2023 came out. It's double in size to what there was about 20 years ago. There's all new features. Rarely something is deprecated or removed from it. It's all added. And there are just more than one way to do things in this programming language. And this is why people hate it. This is why people are so frustrated with it. It's a hard programming language. It requires you to learn a lot, and it requires you to focus on a subset because it comes with so much technical debt, legacy code, and also education material that focuses on all those legacy code. If you go to Stack Overflow and find the C++ questions, you really need to look at the time it has been written to understand if it's a modern solution to the problem. And for lots of things, if you advance the programming language, you can't just say, well, this is how we would do it right now. The ecosystem has to move with it. You still end up working with libraries that have been incepted 20 years ago that you need to use in your programming in your programs, where you can't use modern programming language features. And this leads me eventually to the core of today's talk. Sorry for this long intro, but I think you need to understand where we are coming from to understand why it's important to have those fantastic features in Rust that I'm going to talk about today. So let's talk about Rust. I guess lots of people already talked about Rust and memory management. This is one of the key features of Rust that people love and people adore, and I understand it. It really gives you a totally different feeling about how memory works. Your programs are getting better. Even your non-Rust programs are getting better once you understand how Rust does memory management. So that's something that is definitely a wonderful feature in Rust that I wouldn't want to miss, but this is not what I'm going to focus on today. Today, I want to talk about my personal favorite feature, which is traits. Traits, are the heart of the type system in Rust. And what they basically do is define shared behavior between types. So if you understand interfaces from object-oriented programming languages, yeah, pretty much the same thing. You can describe what needs to be done, and then, well, it will be done, and you can abstract over it. But it's much more powerful in my experience. There are some details to it which make it so useful to an extent which I haven't seen in any other programming language yet. And one thing that I like most about it is that it's also the same means of abstraction for language features. So you can define those traits and you can implement language features with it, which also gives you a very nice segue to introduce new language features. You can define the trait first, you can work with the trait first, and suddenly, with everything implements the trait, you can create a language feature out of it. Let me show you what I mean. This is my go-to introductory example, 2 traits, so you understand it within 1 minute. I'm having here a couple of structs, project and maintenance hours, and I want to define a trait billable. The trait billable tells me, well, I can, charge money for what I've been worked on. Fantastic. And it returns an F42. Then I can implement billable for maintenance hours. Maintenance hours go by a rate and by the hours that I worked on. So I multiply them and return them. Fantastic. I defined the trait, implemented it for my own type. And now I can use it everywhere billable is needed. I can use maintenance hours, and I can call the bill method. This is what it's about. But I can also implement my defined trait for types that I don't own or that I don't have defined. So this is F32. F32. I implement my billable trait for this type that is in Rust. And I just say, well, return yourself. You are an F32 already. Just take it. You are now something that I can build. And this is very simplified here, but it's also incredibly powerful because it leads us, for example, to crates like itertools, one of my most favorite crates. Iterators, design pattern that is, I don't know, 25 years old by now, 30 years old by now, which has found its way into the programming language, is a trait in Rust. You need an iterator to create a for loop, for example, but you also have methods then on your structures that implement iterator. And an iterator comes, with the next method where you get the next item. And on top of this method, you have 70 more methods that make it easier to work with collections and to work with anything that has an iterator implemented. But sometimes it's not enough. This is why there's a crate called itertools, a library called itertools that implements 115 more methods for every iterator that already exists. So somebody said, if you implement an iterator, I can give you more methods. And all you need to do is import this crate or import the one method that you want, and you are done with it. How fantastic is this? So this is something that makes my life so much easier because I'm having quick, optimized methods that I just can add on everything that I have defined. I can define something, and by working with those traits that come from the standard library, my software can be extended by somebody else without any interference. This is so powerful. I'm going to show you a couple of examples in a couple of seconds. Also, what we can extend is language features. So this is actually the one thing that made it click for me to understand, oh, I'm having here a plus sign, but I can define how this plus sign works. I'm having here a clock. The clock stores hours and minutes in U32. I create the new clock, and I'm having here a normalize function. If I'm going above 24 hours, then I start at 0 again. If I go below, you calculate just to have a proper time. Also with minutes, if they are beyond 60, you just add 1 hour and take the rest and put the rest to the minutes, or add the rest to the minutes. It's pretty simple. It's actually not that tough. And I'm having here this add minutes method where I say, okay, if I want to add more minutes to it, then, well, create a new clock with the new hours, with more minutes, it will be normalized, and I'm having here the new time. Probably not the best implementation, but it doesn't matter. It's just moving register around. It's easy. It's okay. It's an okay abstraction for what I want to do. I just don't like the add minutes method. I think it's cumbersome. I want to add clocks with each other. I want to add time with each other. So I take the add trait. The add trait from standard ops with a default generic type parameter. Where I say I want to implement add for clock. And if I'm doing it like that, this self parameter here is also clock. So I can implement an addition for the same type. The output is clock, and everything that I do here is I take the clock that comes in, that myself, and take the hours and minutes from the right-hand side. This is what RHS stands for. Creating on the clock, having a new output, and that's about it. But what I can also do is say, well, I want to add minutes to it, which are represented in U32. So I say, well, implement standard ops add U32 for clock. The output is again clock. So the moment I add minutes to a clock, I still want to have a clock, and call the self add minutes method. And with that, I can create new clocks and add minutes to it or add another clocks to it using the plus operator. Fantastic. What I also did here is implementing the display trait. The display trait tells Rust that this is compatible, for example, with the print line macro, so you can have some output, you can have some display output. You also implement a toString method or the toString trait just with it, because if you're creating a string representation with display, why not having a string representation where you get an actual string? So this comes for free. All you need to do is implement this little trait and you're done with it. Fantastic. And this is how we integrate language features. So we can define add for multiple types, either for itself or for a concrete type for U32 or for anything else that I want, and make language syntax compatible with it. There's another example which is a little bit on the nose, but it's fun, which is this one. Here I'm having two structs, cout and endline, and I'm implementing something that is called SHL for, going into detail what that means for this type and for this type. Oh, what's that supposed to do? Well, if I use it, you might realize what it does. It's basically C streams re-implemented in Rust. So I've used the shift left operator, that's SHL, and implemented it for an empty struct cout. And I said that for everything that implements the display trait, this is here, implement shift left for cout. So everything that can be printed, with println or print, can now be used with this cout struct. And all it does is print it out and return self again, so you can chain those shift left calls. And then I implement a concrete one. So this is a generic one, a generic trait implementation for shift left for this one struct. And here implement a very concrete one, a specialized one, where I say, and now for the endline struct. Here just print /n. And since the trait needs to have some output, in that case, it's both cout. I think you can change it that this will return the empty type whenever. Then you get rid of a couple of warnings, because it's cool, isn't it? It's fantastic. You can implement C++ language features by using the same traits and abstracting over a couple of other traits. How fantastic is that? But no, don't do that. Don't do that. It gives you warning for good reason. It's bogus, but it's fun. And it shows the power. It shows the power that everything that can be printed, everything that can be displayed on the command line is then compatible with those structs that I introduced here, because for whatever reason, I still want to use some C++ stuff in my code. Alrighty. I've talked about that we can implement traits from the standard library for types that we create. I spoke about that we can define our traits for and implement it for types that we don't own. There is this might lead to clashes. This is why there are coherence rules or orphan rules attached to it that tell you what you can actually do. You can define traits and implement your traits for your types. This is easy. You create an interface and then you implement it on your structs or whatever. You can also take foreign traits that come from libraries, traits that come from the standard library, and implement it for your types. Cool. With that, you make your types compatible with other libraries. Fantastic. And you can also implement your traits for foreign types. This is how you make other libraries compatible with your code. But what you can't do is implement foreign traits for foreign types, because they might have a different opinion on what's going on. There are ways to work around it, and we're going to see that in just a second. But those are the rules. Implement traits, implement types. You need to own something. Something needs to be in your possession, so you can implement it then for other types as well. What traits also enable us to do, which is also something that I really, really like, is composition over inheritance. This is one of those design paradigms that you hear for decades now as well. People don't like to extend classes. It's the source of all evil. Having class hierarchies, having complex class hierarchies, just leads to not understandable code. Sorry, this is one of the boldest statements that I did here, and I didn't even say shit. Sorry, swearing number 3. But what do I mean with traits enable proper composition over inheritance? Look at this example. I grabbed this example from Tim McNamara, who does a lot of examples like that. And it illustrates this composition over inheritance example so well. I'm having here a couple of URL strings, and I want to sort them, but not by alphabet. This is what the default behavior would be, but rather by the length of the URL. So if I'm using a binary heap to sort it, I create new URLs, I push it into this binary heap, and when I pop them out, they are being sorted based on the alphabet. So it would be fatblog over GitHub over www.youtube.com. That the binary heap can sort it like that is, so the reason the binary heap can sort it like that is because URL implements equality operators and ordering operators, or equality traits and ordering traits. So what we need to define is something new that works under different rules, not ordering them by alphabet, but rather ordering them by the length of the URL. To do so, I introduce a new struct. The struct is called shortest first. It takes one parameter, which is a URL. I derive a couple of default traits from it, partial, equal, and equal, and also something to just put it out. And then I work on the comparison piece. I need to implement partial ord and ord to say, well, I want to compare those two. How can I compare them? And here I take the left one and the other one, those two that I want to compare, myself and something else. I extract the length of the string and I compare the length with each other, which also now implement ord and partial ord. So with that, I'm now able to use the equality operator. I'm using less than, greater than. I can use all that. I can understand which one should be ordered before the other one. What I did here was creating a new struct where I can compose the old struct with it. This is composition. I take something and instead of extending it and overriding functionality that there already was, because this is what you do with class hierarchies, I just create an entirely new type that can work with the type underneath. I compose instead of inheriting. But to still produce the same functionality like before, I implement traits on top of it that should be there. And with that, I have absolute control what this type should do. There's not just one dangling method that is in URL that doesn't make any sense in the composed value that I can use, because I removed, or I encapsulated all of that by having an entirely new type. This type now works exclusively on URLs, but I can also make it over generic, where I say, well, shortest first for something that can produce a length. I don't know what that would be for something that has a string implemented, because I want to do the length over the string representation. So this might be something where I can have this struct then generic over lots of different types. Composition over inheritance. You compose types and then you define explicitly what they should do. To me, this is incredibly important, because this is where all the problems come from class hierarchies. Oh, I'm using this one method, but it's actually in the class hierarchy, the 5th class that I'm extending from. And then it's gone. And you need to look for it and need to understand what has happened and why it's gone to begin with. Here, it's totally clear what's happening. You understand what's going on. The traits tell you what's going on, what you can do with it, how it works. It also tells you what you can't do with it and where you need to go to the wrapped type, to the inner type to work with it. Everything becomes explicit and clear. And this, in my opinion, is the power of Rust's language design. Everything becomes 100% clear what you can do. So how do you use it if you want to order them shortest first? Well, everything that you need to do is wrap the one type that you already had in those new types. And that's it. Now it works just like before. Composition over inheritance through traits. and through a pattern called new type pattern. So if you ever find yourself reading the new type pattern on Rust, this is what it's about. Alrighty, let's continue. One thing that also benefits from traits is error handling. Error handling, one of the core components of Rust. It's possible with Rust that you write code where you never miss an error because Rust just won't let you. Error handling in Rust works like that. I'm having here a result of u32 in string, which means either the operation succeeded or it didn't. This is all it does. Either it succeeded or it didn't. But then the code is pretty long. So all I want to do is read a number from a file, which means that I need to open that file. That can go wrong. So either I get it or I need to return an error. The other thing is I want to read the contents of the file. Yeah, this can go wrong. So either, yeah, maybe I read it into the buffer or it returned an error. And last but not least, I need to parse the string that I just read into a number. And this can also go wrong. So there are three potential things that can go wrong. And this looks very, very cumbersome, very, very tedious. This is, why people complain that their Rust code is so expressive and so long and they need to write so much. But we can make it easier. One thing that we can do, for example, is create our own error type. I'm creating a number from file error where I can have either a parse int error or an IO error. Those are the two errors that can happen in this particular function. I implement the display trait and the debug trait because that's what the error trait needs. So if I'm implementing the error trait, I make it compatible with the broader ecosystem of error handling in Rust. You don't need to do that. You can use error types that don't implement the error trait. But if you want to make your error compatible with other errors from other libraries or from other pieces of your code, you need to implement the error trait. And with that, also the display trait and the debug trait, so you can show them, you can display them. Then I implement conversion traits. I say, well, if I'm getting a parse int error, then I can convert it into a number from file error by using this one enum variant. Same with the IO error. If I'm getting an IO error, I can create the other enum variant. That's it. Now I can convert every error that happens in my code to one error that I defined on my ROM. And with that, all I need to do is change the signature of the function. I'm now returning a number from file error, not a string. And with that introduction, I can bubble up all my IO errors. I don't need to handle them. I just say, well, if anything goes wrong, return a number from file error. And I can also return the parse int error through the question mark operator. If you look at it, this is the happy path. You just write code that is supposed to work, and all the error handling is being done somewhere else. It's still safe. It still doesn't produce any unforeseen values because you need to handle the error, but at a different place. And your code becomes readable, becomes clear. It becomes painfully obvious what's going on there. And if you see something like number from file error, you understand, well, this is a custom error. I look into it and see what's compatible with it. And you don't need to do that. You can also say, well, take a trait object that implements the error type and you're done with it and never deal with the exact error. But, your mileage may vary. It might totally depend on what your project is actually about. Also, this question mark operator is implemented through the try trait. It's now experimental, but guess what? There's a trait for syntax in Rust, and both the option enum and the result enum implement this try trait. I put the RFC to the try trait into this talk. Read it up. It's beautiful to see how this error bubbling is implemented through a trait and how it enables the Rust team to add this question mark operator. It really shows you how abstracting something in a trait and creating language out of it works together. Yeah, I guess you realize that I'm getting really excited about that. Same if I talk about, this is kind of my shtick. I'm talking about refactoring a lot. This is where I come from. We have lots of Rust projects in Rust at Dynatrace. And Rust is a really good language to prototype because you can cut corners, but it becomes very explicit where you cut corners, which means that at one point in time when you prototype, when you just scribble down whatever you got, you can take your time and refactor nicely into something that's much more maintainable and much more readable. And this example now comes from a little app that I have written where I just store key value pairs in a database. It's a hash map, basically. But look at what we're doing. So it's a web app. You can either take some value, whatever value that it is, and store it in a key value pair. So you are getting a key, which is here, and the value, whatever that value is. So I'm also storing a content type here to understand if it's an image or if it isn't. And this might go wrong or it might not, but everything that I did is I'm taking the shared state, take the database, insert a key, the content type, and some data. And then I can get it again. So if I'm getting the key, I say, well, is this key available? If it's available, read out the content type, read out the data, and return the value. Otherwise, return a new status code not found, key not found. This is based on a framework called Axiom, one of my favorites. Everything that it needs to have is having an into response. So everything that implements into response can then be converted into a proper HTTP response. This is what's happening here. Otherwise, I'm having a key error. I'm coming to the key error later on. It's 4 lines of code, so ignore the lengthy header of the function signature. What's going on really is just a couple of lines of code where I write something or I return something. So far, so good. Nothing to worry about. But now I want to have, a little bit more. I want to have more functionality. I want to create a grayscale endpoint where if it's an image, if it's a PNG, I want to convert it into a grayscale image. That should be one feature of my key value store for whatever reason. And it already takes a little bit more time. So first of all, I need to read data from the key value store. And if it doesn't exist, I need to return a not found error. Or I need to say, well, if it's not an image, I need to return a forbidden error because all I can do is convert PNGs. Maybe I can extend it. But if it's not convertible into an image, I need to react on it. So error handling here. Also, I need to load the image from memory into a dynamic image. So what comes out here is a dynamic image from the image crate. It's a struct from a different crate. This might also fail. I'm doing unwrap here, which means that my program will break if I'm doing something wrong. Not what you want to have. If this loading of the image data worked out, if we got there, great. Then I'm having a new image, which means that I create a new vector of bytes and I create a cursor into it. This is happening here. Then I'm taking the image, call the grayscale method, and write everything from the image in the output format PNG into my vector. So the image crate stores it in some different data, and I need to get bytes at the end that I can send out. And last but not least, what I do is I create a new response with the content type image PNG and create the newly created bytes out of it. It's a lot of work. It's a lot of work to, modify data to make sure that the data is compatible, and it's a lot. It's a lot. But I want you to focus on this particular line here. I start refactoring this line because it has string values into that. I don't want to be bothered with string values because they can introduce all sorts of bugs if I get them wrong, and rather want to work with something called an image response. I want to work with a response that where I know if I return this, it will be an image. So what I create is I create another struct. I implement the constructor here where I say, well, all I want to do is I want to get into bytes because I'm sending bytes. So if I'm adding here a vector of U8, it can be converted into a byte array. This is why I'm creating this constructor here. And then I'm implementing the into response trait from Axiom for this image response, where I say, well, once you have this image response, I can create something that is of content type image PNG, the bytes, and return it into a response that Axiom can work with. Fantastic. So instead of having this huge OK and tuple and whatever, all I do here is saying, if you can convert it into bytes, then you can be an image response. Please send an image response. Cool. Works. I created my own type. I applied a foreign trait. But what I can do now is also convert from a foreign type into my type. I implement the try from trait for the dynamic image from an entirely different library. And here I say, okay, well, it can result in a key error. What the key error does, I'm going to tell you in a second. And I call image response try from with a reference because I implement the same thing for a reference as well. And the code that's coming here is creating a new vector creating a cursor into it, write it into that data with image output format PNG, and create a new image response with that vector. So by creating this struct, by creating the boundary that you need to have bytes to be a proper image response, I can now create a conversion trait from a dynamic image into this particular struct by applying more traits. I also have the KV error, that's a key-value error, where I say, well, if I'm getting some image errors, because that can happen now when I convert, I can return batch requests or not supported or whatever. I can do that here in the from image error to KV error thing, the same error handling that we had before. And now a bunch of lines of code are reduced to this. I say, well, if it works out, create the image response from this image that you just created and make it grayscale. That's all I do. That's all I do. I just say, I want to have an image response from that image in the grayscale format. Fantastic. And I can use that now for many, many more functions. If I want to resize it, it's the same line. I just say image.resize. If I want to skew it, to change pixel, to invert it, to apply a sepia filter, whatever, it's the same line. I create an image response from that image that applied the method. And it's a little bit of refactoring, just applying a bunch of common traits to it. And your code becomes so much more readable and so much more usable. I'm still a little bit bumped by the whole, is it available or not thingy, which means that I'm going to change my database. I'm going to change my stored type. Instead of just storing some bytes in a content type, I say, well, all I want to do is either have some bytes, and I don't care what those bytes are, or to have an image which I want to convert into a dynamic image before the fact. So when I store something now, I'm having here this post query, and I say, well, get the stored type with get stored type of the content type, and I either create an image where I already converted the image into a dynamic image. So this already happened. Otherwise, just stick with your types and store this enum into my key value database, which means that now when I'm calling grayscale, all I need to do is check, is it an image that I can work with? Then create an image response in grayscale. Otherwise say, well, the key has not been found, or the key can't be converted, or whatever. And now it becomes obviously clear what it does. You refactored a huge pile of code into something that's easier to understand, easier to reason about, where you have types that tell you a story, that tell you what's going on there, and functionality that you can reuse for multiple endpoints as well. One last bit, one thing that I also liked is transitive trait implementations. This is also very great. I'm having here a shared state, a custom type that I created that implements an arc. Arc is an atomic reference counter used for multithreading if you want to share the same thing across multiple threads, with an RW lock, which means that I want to have exclusive write access to the data with the app state that I just created. The app state is this one hash map here, and all I do is I derive the default trait from it. Now, the default trait, what it does, it creates a structure with default parameters. That can be empty parameters, just creating the memory or whatever. It doesn't matter. It just says, well, that's the default constructor. That's what you should get if you don't add any parameters. Now my app state implements default. Hash map implements default. Arc implements default. RW log implements default. And now I can create a type alias where I can create a new app state with a new hash map in an RW log in an ARC by just saying share state : default. They all implement the same trait. And with that, I can make sure that I'm creating an object with all those helper types. It's ARC, RW log, app state, hash map, just with one line of code. Sorry, I'm getting really excited about it. All right, I need to talk a little bit about async Rust. I don't have time to go into detail. I can, if you like, at another time. But it's also, again, about language features. And this has been tried and tested, and you could really watch the Rust team working on that. Rust has async in the wait support. They don't have a runtime built in, which means you need to add the third-party runtime to make async in the wait work in your Rust application for various reasons. But Rust decided to create the future trait. And with that future trait, you make, first of all, async await as a syntax compatible with any runtime, but you also can abstract over that future trait to work with potentially any runtime. And this is also something where you can really see how a trait at the core of a language feature managed to create an entire ecosystem of Rust libraries, Rust code, frameworks, etc., and syntax, obviously, by focusing on the proper design of one single trait. If you want to learn more about async Rust, please don't hesitate to catch up on me. I love to talk about that as well. Alrighty, now I'm wrapping up. To wrap up, there's a lot of stuff that I have left out. First of all, I didn't go into the details of async. I'm sorry about that. I haven't spoken about reflexive trait implementations. You can implement the trait based on the implementation of another trait. How cool is that? I haven't spoken about the power of trait bounds. I haven't spoken about trait objects, and I'm pretty sure I left out many, many more things. What I also left out, a little down at the end, I need to structure my talks better. It's not all roses. Traits can be very complex, especially if you go into async. It can be very complex, which also means they create very complex error messages. Rust is well known and loved for its error messages. But if you have huge complex traits in there, they don't help you at all. You need to have helper libraries that tell you, well, I can interpret the error for you and tell you what's actually going on. But this is being worked on. So people around the error handling group are working on improving those error messages. Also, don't mistake traits for interfaces. They are not interfaces. They're not interfaces. They are much, much more powerful, and they have other limitations. Personally, I feel that trait discovery is still a little bit of a problem. You need to understand the documentation good. A Rust analyzer as a tool helps great discovering traits, but you need to understand that you need to look for them. And at one point, you realize how traits work underneath, and you can read them, but until then, they can feel a little bit like magic. Which brings me to the conclusion. Traits are an integral feature of Rust, not only to abstract behavior, but also to design language features. And this is why I think, going back to why everybody hated C++ and why I think nobody will hate Rust in the future, not more than they already do at least, is that we have one central construct, one central feature that allows us to define new language features and boil it down to the same thing. And I think this is immensely powerful if you do language design. You can define everything through a trait. They can be experimental, that's okay, but they can also be open up and extended if they are seen robust enough, which helps you creating better libraries, which helps you creating better code, which helps the language team, the people who work actively on Rust and pushing Rust forward, helps them creating new language features so they don't interfere with your existing code. First comes the trait, then comes the language feature. And you can always start by working against the trait instead of trying to move an entire ecosystem with it and decide on a language subset, because the subset is a trait. And traits will become more powerful in the future and will be more usable in more position. Type-alize, impletrait, return position, impletrait in traits, hiring trait bounds, and generic associated types. I know what those acronyms are. I can also explain them to you, but at another time. So yeah, everything that comes up will center around traits, which wants me to close with another phrase from Saint-Exupéry. This comes now directly from The Little Prince. Words are the source of misunderstandings, and I want to add to it, but traits are not. Traits give you a lot of understanding on what's going on in Rust. They give you a lot of understanding what's happening in your program, in the standard library, in other libraries. Go learn them. Do yourself a favor and spend some time with them to understand what's going on. It's absolutely worth it. And with that, thank you very much for your time. Thank you very much for being with me. And I'm open to all your questions.
Stefan, hello again. Thank you so much for the talk. Also for the Little Prince references. Love them.
Yeah, they're cheesy a little bit, but it's I couldn't resist mirroring C++ with the Little Prince. This was just a joke too good to be true.
They're not cheesy, they are iconic.
Yeah, absolutely.
All right, Stefan, we still got some minutes left, and we got some questions, and I would say let's tackle the first one. which would be, how does Rust's trait system influence code testing and debugging practices? Are there any strategies or tools to help with debugging?
Okay, so there's one thing that I had at the end where I think that, especially in compiler error messages, traits can add some complexity that is hard to handle. For example, in Exum, you need to work with a very huge service trait or handler trait, I guess it's called, which can produce a page full of generic nonsense that's really hard to decipher. And what Exum does is adding the debug handler macro so that you get better error messages. But Exum is able to add the debug macro because of traits. So this is good. I think in terms of testing, what I did at one point is there are mocking libraries, of course, but it's also very easy to create your own mocking library if you introduce a trait on different structs. So, for example, I have one web application where I'm using an actual Postgres database to store values in production, but I want to test my handlers against a simple hash map key value store or file-based anything where I can prepare some fixtures. And I abstracted that through a trait, and this works really, really well. Especially, I don't know if it's also possible in other web application frameworks, but especially with Exum, I think it's really, really great to create an artificial request on the outside, send it through the stack of Exum, and get a result, and then evaluate that result through something that you defined on your own, like a key value store as a database. And the reason that's possible to do so in Exum is also, again, through traits. So I think the influence is implicit. Since everything centers around traits, it's totally up to you on how much you want to leverage them. But I think they can be very powerful and useful as well. I hope this answers your question. And if it doesn't, there's one. So I'm also working on Shuttle Launchpad with the fine folks at Shuttle, which is a almost bi-weekly newsletter where I work on little applications, and we spent one issue where we show mocking and testing. It's on shuttle.rs/launchpad. You see it there by example how you can use traits to mock, to test, and hopefully it helps you also with debugging. Yeah.
Thank you, Stefan. Next question is connected to the last one, and just maybe to give some examples. You referred to some tools to help trait debugging. What are they?
And yeah, so that was the Exum debug handler macro. Yeah, but okay, that's from the Exum project. Other projects have different ways to help that. Yeah.
All right, but this is like your go-to.
Yeah, sorry. Yeah, for the Exum framework. If you want to debug traits on its own, they are just a description on how the interface, quote unquote, should look like. So there's not a lot to debug, but you can also have default implementations on those trait methods, which means that you can debug them, but at a breakpoint there, hop in just like you would do with any other tool as well.
Right. Thank you, Stefan. Next question. For new developers exploring Rust libraries, how can I spot well-crafted traits in external code and use them in my own projects?
Yeah. This is a very good segue to Luca. I know that Luca is coming up next and he talks about Rustdoc. Start learning to read Rust documentation. Rust documentation is fantastic because if you see a type, you also see which traits it's implementing, and you can click on them and you can see how they implement the trait, but you can also click on the trait and see which other types from other libraries are going to implement the same trait. And this is a very good way to navigate around what's happening. And the trait is well crafted if you can abstract a lot of behavior in the ecosystem really, really well, I would say. So it's actually tough to say, is this a good trait or not? We are going into a territory where we go into how can we abstract stuff and how can we reason about stuff and what's good naming. What I would suggest is starting to learn the traits from the standard library first. Especially conversion traits is something that you need to look into, and ops. There's standard ops. I don't know where the conversion traits are being located at, but you're going to find them. They're called into and from. See how the default implementations are going to look like, and you learn a lot from them. And if you understand how they work, you can take this knowledge and put it to other libraries as well.
Right. Thanks for giving insights on this as well. And we jump to the next question, a very friendly question. In what sense are traits not interfaces smiley?
First, you can have default implementations on traits. You can't have them on interfaces, but you can have them in abstract classes. Then you can apply trait bounds to them, which limits the usage of your trait to a particular set of types that also implement another trait, which is, I think, very powerful, especially opposed to if you have interface hierarchies or class hierarchies. You can just say, you only work if another trait is also implemented as well. And for this method to work, I need to have another trait implemented as well. And you make cross-references to other traits instead of hierarchies, which is arguably in the end much, much easier to reason about. And for me, the biggest difference is that you can implement your traits for foreign types. You can make code by other people compatible with your code by just defining a trait and implementing it. And if you understand how the iter-tools package works and how it works and applies stuff to every iterator that existed and will ever exist, this is mind-blowing. It's such a small detail, but it's mind-blowing once you understand what you can do with it. So, yeah. And interfaces are boring. Sorry, they are absolutely boring.
All right. Thank you, Stefan. And we still got time for one more question. Let's see.
It's great that you have so many questions. I loved it. Yeah.
As a dev coming from a language without a trait system, what mindset changes should I make to make use of traits in Rust?
This is a very good question. It totally depends on which language you're coming from. I think types in TypeScript are more alike to traits. It hurts saying that, but there's a little bit of truth in that. Are more alike to traits in Rust than, let's say, an interface coming from C# or Java. I think the one mindset that helped me really is that you have two levels. You have on one side the actual values that you have, which are structs, enums, whatever, or primitive data types. And on the other hand, you have the possibility to define behavior on top of them almost independently of what struct is underneath. And with that, you can separate the actual data from how should they behave in a different context. And this mindset helped me a lot, because then you understand you can design software purely based on traits, and then just in the end have this one actual value that works with it. Or you do it the other way around. You define values through types, through structs, enums, whatever. And once you want to have it work with other parts of your system, slap as much traits on top of it to make it work. So yeah, that's the best I can do. giving that minute.
Yeah, thank you, Stefan. We got one more question, and I think it's a very good closing question. Okay. So maybe let's tackle also this real quick. What is your favorite thing about Rust, and what are some features you still miss? I mean, okay, maybe this is a whole talk on itself, but
it's absolutely traits. And I'm in love with error handling. I love traits. What do I miss? I've given you a list of features that is currently been working on, right? Return position, infiltrating traits, type aliases, infiltrate, etc. They are actively being worked on. Everything that makes a simple infiltrate usable in many, many more positions where I don't need to have a concrete type, but just can say, well, here I want to have anything that implements the trait. I want to have that, because it opens up much possibilities of abstracting your code. So yeah. But yeah, you know, what's your favorite thing about Rust? Kids, I'm still in the honeymoon phase with Rust after 3 years. It's so much love. I love all about it, of course. So yeah.
Could also
when this honeymoon phase will end.
Yeah, could also be a good title for our next talk, like 3 years of honeymoon with Rust.
Yeah,
What I learned
absolutely.
in this relationship. Nothing like that.
Perfect.
All right. Which confirms that you will attend the next Rust Day also.
Oh, I hope so.
So, yes.
Yeah, cool. It was a lot of fun.
Right.
Thank you very much.
Pleasure all on this side of the camera. Thank you so much, Stefan. Thank you so much for joining us today. Thanks for the talk. Thanks for the Q&A. To the audience, if you still have some questions, just reach out to Stefan on his socials or everything. So he will gladly answer all of them. And Stefan, as we already have the title for the next talk, I would say till the next live day.
Fantastic. All right. And have fun with Luca. He's amazing. He's a good friend of mine. He's going to rock the stage right now. Alrighty. See you. Bye-bye.
See ya.